How's it going? Hey, Frank. How are you? We'll
Yeah, I'm
kind
doing
of
pretty good.
give some time for folks to hop in. Where are you based today? Are you in the South Bay?
We're in our office, so we're in Redwood City, Redwood Shores to be precise. So right in the middle of the peninsula, right between Sunnyvale and San Francisco. So
Awesome.
yeah, if anybody's around, feel free to hit me up. We can grab a coffee, do something along those lines.
Absolutely. And what's is it warm out there today? Is it like cold? You got
Honestly, like yeah, it was actually cloudy this morning, which I was pretty surprised about. But aside from that, yeah, it is warming up, and in particular, this room, it gets so much sunlight right around noontime and in the morning as well that it ends up getting pretty warm in here, even with the air conditioner on. So, not a bad thing, but it is quite nice. That's one of the reasons I love the San Francisco Bay Area, right? The amazing weather.
Here's a side question for you. Where do you think the center of Bay Area AI is? Is it San Francisco these days? Do you feel like it's the peninsula fighting back? What East Bay?
It's definitely San Francisco.
Yeah.
100% San Francisco. So I'll go up to San Francisco every now and then to attend some of these meetups, some of these events, but it's definitely San Francisco. Are you familiar with the Cerebral Valley meetup spreadsheet?
Yeah, I have seen that. Yeah.
If you look at that one and you look at the location, San Francisco is by and large just everything's in SF, and it's not even a close second, is actually remote. So I suppose make of that what you will.
Have you been to so those who you just joining, we're talking about the center of the world AI. And have you been to any kind of meetups in the Valley recently? I mean, are people is it just not happening as much, but still happening down there? Mountain View, Palo Alto.
It still happens. So last week I went to one hosted by Snorkel. Yeah, that one actually had quite a few people. So I don't think it's that there's people who don't want to go to these meetups in the peninsula.
Yeah.
It's just that they're just not as popular, right? And there are also a lot of great meetups in San Francisco, period. So one of my favorite ones is actually the ones with Arize and with Ray. Both myself as well as our developer advocate who went there. But hopefully we see a bit of resurgence in the peninsula here. It's just not as active right now, but we'll see.
Awesome. Well, do you want to introduce yourself? Feel free to introduce yourself and tell us.
Yeah, no, absolutely. So hey everybody, my name is Frank, and officially director of operations as well as ML architect here at Zilliz. And at Zilliz, we are the creators of Milvus, which is arguably the world's most popular open source vector database. And as a part of the Milvus community, I think one of my key goals is to encourage the adoption of a variety of different embedding models. And I have, I sound like a nerd saying this, but oftentimes I'll train my own models over the weekend. And really see what some of the, really see how the performance of these different model architectures, enables, let's say, different activities, particularly in computer vision, right? So it's only recently, probably in the past year or two, that I've gotten a little bit more into natural language. But yeah, it's a pleasure to be here. Thank you for inviting me, and looking forward to getting this paper reading under the way.
Yeah, no, excited to have you, and we'll do more of these for sure. So, and those of you who don't know me, Jason, co-founder here at Arize, I would say also somewhat of a kind of a nerd hacker and touch and build this stuff as much as I can. Just it's something I just love doing. So this one is this paper is a fascinating one where we're going to go between a little bit of a blog and a paper. So this paper was written by Facebook but the Meta team, but was kind of jumped. A hacker in the LLaMA community kind of hopped ahead of kind of the results of this one with an amazing story of them discovering this issue. And it's really in this abstract area around positional embeddings. And, Frank, had you thought about positional, have you looked at the positional embeddings before? And, had you read papers prior to this?
Oh yeah, absolutely. And the concept of positional embeddings for folks. Well, actually, here, Jason, is it cool if I share my
Yeah,
screen here? I just
absolutely.
do. I don't know how we. Give me one sec. Whoops. I'll just share my screen here. But the whole idea, I think it was very, very difficult for me to understand what the, coming from the perspective of computer vision, it was very difficult for me to understand what positional embeddings were really there for until I get a better understanding of how these attention scores work. And in particular, I sort of want to draw this diagram out, and then I'll hand it back over to you, Jason. But in particular, if I have the way self-attention works is that there is, you maintain what is effectively this large, self-attention matrix, right? So it looks something like that. And each sort of axis corresponds to the same sentence. So it's always a square matrix. So it could be, for example, a, large, I don't know. Okay. Let's ignore that for a second here. But effectively, each dimension is a word, is a token. I'll call them A, B, C, D. Whoops. What is going on here? B, C, D. I don't have my pen here, so it's a little bit harder to see. And what we are really interested in doing is computing these attention scores between all of these tokens. So in particular, when it comes to transformers, if I were to swap any two of these, so if I, for example, if I swapped B and C here, and instead it was C, B, C, B, you'll notice that my attention matrix is also, these two dimensions are also transposed. So I really lose that positional information. And that's really where positional embeddings come into play. And in particular, for the original transformer paper, what they would actually do is you essentially have these multiple sinusoidal waves. So it might look something like this. And then I have a higher frequency one, and then I have a very, much higher frequency one, and then I have a very, very high frequency one. And they sample at these linear intervals, these high dimensional waves. So I might sample right here, 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 and here. And the concatenation of all of these values would give me the positional embedding at a particular token. So these are called absolute positional embeddings, right? For the reason why you need positional embeddings is because you lose that information without them. And when it comes to, these embeddings can really seem a bit like black magic. For the original vision transformer paper, I believe they're just additive embeddings. And really, it shouldn't work if you think about it from a theoretical perspective or even an intuitive perspective, but it does, right? And that, I think, is one of the amazing things about deep learning in general, which is that you can have so many of these you can do amazing things with backpropagation. You can do amazing things with these different model architectures. But I'm going to erase this. That was a bit of a long-winded answer. I apologize about that, Jason. I'll sort of stop my sharing here and hand back to you.
That was great. And I think I guess the big picture, the biggest picture I take away from this stuff is that there's basically you're saying to make transformers fast, to make them much faster, and ability to do stuff in parallel and have over maybe what was your RNN previously, you lose that positional information, and then essentially the these positional embeddings kind of add a little bit of that signal back. So the models can kind of understand a bit of the order of the words, which you kind of lost in the transformer architecture, which I think is like the big point you're making.
Yep.
And what's so interesting, I mean, what was so interesting about this is that if you have them, and the core problem right now, what people were trying to solve right now was like, you've got this model trained on this small context window. Why can't I extend that window with fine tuning? There's
Yeah,
just like, I should be able to like take a model that's trained on something small, but extend it. But you'll see from a lot of this that like things were just breaking in very non-obvious ways. And walking through a little bit of the blog, I think you'll see
yeah,
the confusion everyone was having in the industry. And I think what you're going to find here is a very subtle issue with positional embeddings that was causing a myriad of experiments and problems and things across a lot of different papers. And so the question is really was kind of this: can we extend the context window of an existing pre-trained LLM? Can I take that, can I take 2000 token and bring it to the 16 or 32 from the current LLaMA versions I have? And kind of, can I take a fine-tuned transformer, extend that context window? And in this work, they introduced this concept of position interpolation. There's, you see this idea of interpolation versus extrapolation as kind of coming in throughout the paper, where you use some of the you use signals in an area that the model's seen before versus signals outside of that area, and we'll talk a bit about what that means further on here. As you go through, I think this was kind of your drawing of
yep.
a good drawing of the positional embeddings and the regions. Do you want to talk a little bit? I mean, this might be a good one just to speak to.
Yeah, absolutely. And I was very, before I go too deep into this, I was very surprised that this paper in particular actually didn't cite the original vision transformers paper or even the data efficient image transformers paper. And I'll go a little bit into that. I'll go a little bit deeper into why I think that is, right? But in particular, what you see here is if I have a context window of, let's say, size 2048, or it could be size 512, and if I try to extrapolate the positional embedding, so we were talking about those sinusoidal waves a little bit earlier, right? And how the positional embeddings are effectively these multi-frequency sinusoidal embeddings that I simply sample at these individual intervals. If I try to extrapolate into that unseen range, and maybe we actually want to go to that, there's another graph down at the bottom where if I try to, it shows the attention scores in addition to the
Yeah,
right there, right here. Yep. And this was very, this was looking at this, it really just clicked to me because in particular, if you look at the effect of extrapolation, you can see that the attention scores go wild. They go crazy, right? So whereas they're mostly bounded between 3 and -3 went for the context window that I have trained, if I try to extrapolate those sinusoidal waves, I end up getting these positional embeddings that the network has never seen before. And that causes the absolute value of my attention scores to go, well, first it drops off a cliff and then it goes to Mars, right? So
I mean, it's absolutely
not,
I mean, you're -3 is the normal range and you're in 8,000.
Yeah, absolutely. It goes crazy. But instead, if I look at the interpolation, right, if I look at the effect of interpolation on these attention scores, I can see that they are much, much more well-behaved and that they're very, very bounded. I know it doesn't really seem like that unless you look at the scales, but the scale for the graph on the right is negative 0.2 to 0.2, looking at those positional differences. And that is where I think that is a key contribution of this paper. If we go back up to that diagram up there, there's a I think this is really, it's honestly an incredibly simple idea, and I'm surprised that it works so well. I'm not surprised that it works so well, but I'll get into why that is a little bit later. But if we have this range, if we have this context window in the in the pre-trained area, and then what we do is we want to extrapolate that into this unseen range, that doesn't work that well. But if instead what we do is we interpolate it, now you can think of it as sort of squishing the, really just squishing the range of these sinusoidal waves that we've seen, or the range of these positional embeddings that we've seen. So now instead of, as I do the fine tuning, a token at position 4096 gets interpolated to what the original model considers a token at position 2048. That ends up working much, much better, and that gives us much, much better performance. And I think if we look at some of the stuff down at the very bottom, some of the results, I think it goes into that a little bit deeper. And they also have some proofs in here, which we can go over as well. But it's very, I think I've come to an interesting story for folks here, and I'll try to make it quick because I know I only have 30 minutes left. But back when I was on the computer vision and machine learning team over at Yahoo, we would do these paper readings, and there was this one paper reading, I think it was on quantization aware training. I think it was in like ICCV 2015 or something like that. And where they had like this long proof of how quantization aware training, how it is the optimal way to do things, right? And I realized at the very end that what they had really done is they had taken the result that they wanted and they worked backwards to derive it, if that makes sense. So I'm a bit wary about a lot of these sort of proofs, especially in machine learning. In machine learning, oftentimes you'll have proofs that don't necessarily translate to something that's actually practical. But that's a story for another day.
And I think this is like kind of the meat of it here too, which is kind of three things. It's pretty easy to do with a pre-trained model, which is kind of step one here, not requiring that many steps. The position interpolation generates strong results, which make use of the extended model. And you see that in the results where they have kind of a couple different tests where they test these extended model windows that were fine-tuned on. And lastly, the question might be, does it degrade performance in the thing you originally trained on, that current window? And it's a slight degradation, but actually really, really small. So works really well is kind of the takeaway here. The thing I wanted to highlight too, so people believed this was possible,
Yep.
but they really were running into a lot of issues. And there's this concurrent work, which is this blog, which is amazing. I mean, it's just worth a read. It's such a good example of how hard it is for someone to. It's just a great story of troubleshooting, and I'm actually going to pull it up. But it's like all of this paper, kind of all of these papers typically hide the hard daily work that goes into like troubleshooting a really, really tough issue. And I think this blog kind of hits on those issues. I think a lot of people thought this could happen, but no one really knew what was going on. So let me bring this up. So Ko Kendev, so I don't know if I'm saying it right, is the person who wrote this up. And it was just like his story. So he kind of notifies that, Meta has to reference. So basically he wrote this up, then Meta's paper came out, had to reference this blog here, which kind of hit on the same things that the paper hit on. And which is amazing. You got this LLM, this LLaMA hacker doing amazing work here to figure out what the problems were in a very thoughtful way, and coming to the same conclusion of an entire team at Meta. And so the problem is this, like, he just talks, he goes through, how he really would start to think about like extending the sequence and like, well, what papers define the problem? And there's quite a lot out there. There's like why it fails. Maybe it's distracting tokens. Maybe there's bias, in terms of positional embeddings. There's a bunch of these where they propose fixes, during long reposition embeddings are updated much fewer times. They add padding in, but don't get that big of a difference. So just, I mean, community-wise, people are kind of stuck on this. You feel like lots of different people are trying to figure out why this is happening. And he's kind of reading and trying to figure out like what he should do to test some stuff. And he's like, okay, I have a better sense of the problem. What are some remedies? And there's some around like, stuff you might do in pre-training. There's some of these that like have to do with demonstrates a real fine tune.
Yeah.
By changing attention. I mean, there's just a bunch of like shots at fixing this that he's trying to
Yeah.
figure out. And anything else to add, Frank? I'll keep kind of going here.
Yeah, no, I think all of these sort of papers and all of these strategies have their own merit, and these ideas are, I don't want to sort of take away from these ideas in and of themselves, but oftentimes you can think of them as more of trying to build atop of what there already is, rather than looking at the core or the crux of the problem, which this person goes into. It's a great blog post, which goes into talking about how we compute attention and what the role of the positional embeddings are themselves. They go into some potential solutions down there, but there's actually one line where they highlight a little bit, where the author highlights, and I feel really bad for skipping over all this stuff, but if we go a little bit down,
a lot of work here. I mean, just a lot of thought, a lot of work.
Ton of work.
And
ton of work.
in these.
Yeah.
And then he gets to the very end here.
Oh yeah.
Like the different things he does to try to test these and reproduce and get these, and just keeps getting like insane results. And the insane results are like and it's not just like you saw those intention values explode. The models were not just getting slightly worse, but seemed to be getting much worse the more you'd go over your window length. And so just these very unexpected results, it sounds like what was happening as it was occurring. And he gets to a spot where it's like, all I can think of is like, I got it upside down. Yeah. There does not seem to be any reason why the predictive model cannot extrapolate, but it can't. And then he's like, well, I was thinking it wrong. Maybe there's something preventing it from doing so, or suppressing the behavior in it, which is kind of like, okay, now let's start from basics, which is, a lot of us have done this debugging a million things. Let's kind of rip everything out and just start with something simple. Which is kind of what he did here with just went to this sliding mask approach, which is, I guess a part of a long former paper kind of uses this, but just try to keep the window in a more fixed length but use a very simple, just basically simplify the problem. And still getting to a spot where, things weren't working. And then put simply, he's got a hunch, gets a hunch that the model's kind of understanding the positions or learning the positions, and basically causing problems when you're applying positions outside of the stuff it's learned. And so comes down to this, well, let me do position IDs, and own, but keep it fixed in the range. And then voila, he's got some, something that works, and kind of comes to the same final approach as the meta paper, which is amazing. So just an incredible debugging, hacking job, and goes to show what LLaMA's open source is doing in the community too. I think having the ability for an individual to tackle this just wouldn't be possible without that. So we'll come back to the paper and kind of go through the results here.
Yeah, but I totally want to echo what you said, Jason, talking about LLaMA. I think open source, irrespective of what OpenAI or Anthropic, or any of these other sort of proprietary LLM vendors say, I think open source definitely has a place in the broader AI space today, right? And the reason is because you see hackers like Kaio Kendev. Again, I don't know if I pronounced that right. I apologize, Kaio Kendev, if you're watching. But you see these amazing engineers like Kaio Kendev who are able to hack on top of LLaMA, who are able to hack on top of these LLMs, and come up with these amazing results that generally, in a typical sense, would be reserved for these large, well-funded research teams at big tech companies such as Meta, right? And I think that's really the amazing. It's really amazing. It's really amazing. I hope we see more of it.
Yeah, I agree. And I do think with the LLaMA 2 license moves, you're definitely kind of having them going more in that direction. Now we get into a little bit of the tech, a little bit of the math behind this. And I think it gets at like, from an equation perspective, I think the core takeaway is kind of what you're hinting at here, which is they turn that they turn that embedding into something which adds in a, you know, that kind of positional embedding signal, sinusoidal or really a complex, which also can be represented by a, you know, complex number, which is what they kind of create here out of that embedding position. And the point of this math is just to kind of show that, I guess, the tension should be based upon relative position, which is kind of the goal of the positional embedding itself. The attenuation of attention should be based upon that. And I think that's kind of and then I think they talk about here, well, attention score depends on relative position. So the point is just, I don't think this is new. I think they're just kind of highlighting that first before they start to tell you like why it might explode, even though this equation kind of holds. So rope only depends on, you know, relative positions, but extrapolation performance is not great. And it's really like, you know, the unseen values of this function outside of this range is kind of what causes problems. And it says, you know, that kind of like that you're going to see kind of these bounds being held for probably the region of area you're trained, but probably the bounds don't hold outside of it is kind of the point they get to in this section. We see catastrophic issues beyond you know, a certain location, and what is the reason behind it? How could this happen if attention score decays relative to this? So that's the kind of point they're making. There's this hard equation above that's supposed to, like, you know, say attention decays in some natural way, but yet, wow, I've got this blow up right here. And they go on to like theorize a bit about why this might be true. Is kind of was my take. It was it didn't feel like a hard proof necessarily. They talk about like how the positional embeddings can act as like a set of basis functions, and those basis functions can represent any possible function in this range. So those basis functions could look great and represent something really, really well in that range, but can look very different outside of that range. Was my very high level take of what this section's trying to get at here, which is just a possible explanation for why things fit well in this region but don't fit well outside of it. And then they talk about, you know, the solution, which is funny enough, Kendev's exact same solution. Both came to separately, independently, and it's basically interpolating and fitting those points into into the window. It's a very simple change. And what's amazing about this is you don't need to change LLaMA. Like, it's not like a pre-training change. It's simply the LLaMA it's simply use the LLaMA models out there and make these adjustment, fine-tuned to extend the window, and voila, you've got something that actually is, actually works. They do, this is again deep in the math section where they're just trying to like talk about why there's some really good bounds to this, trying to justify again why they're not going to get that big explosion like you saw in that picture, and the positives of the architecture. Talk about fine tuning. So what's needed to extend that window. And then they did talk about, okay, maybe there is some ways in the future we might extrapolate. You might be able to add some regularization so that the extrapolation could be used, but they actually don't do it, don't test it. And given how well this works, I don't know how when we'll get someone doing the extrapolation anytime soon. But they do hint that this is an area of looking at. Experiments I thought were pretty good. I don't know if, like, as I looked at it, like the results, I mean, showed the two things in my mind. Like, it didn't degrade the stuff in the small window and seemed to work, use the large windows is the takeaway from these sections. Got, except for rescaling position indices for models extended. A little bit of the training procedure.
Yeah, I think you see, especially in some of the numbers, you see that as they use their method here in the paper, as they use PI to do the fine tuning, yeah, right here, you can actually see the perplexity scores decrease for those longer context windows, which I think is pretty unique. Now, if you use just pure fine tuning, so in all those columns that say in all those rows that say FT, if you use pure fine tuning and you try to extrapolate those positional embeddings rather than squeezing those waves and doing interpolation, you actually get worse results. So your perplexity increases, even though your context window increases as well. So definitely some great results here. And I think it sort of shows the power of interpolation.
Great. And I think there's one
Sorry.
question here in the chat. I don't know if you see it, Frank. So it says, I love Fourier analysis. I'm a mathematician, data scientist, and a Google partner here in Brazil. Do you think there's some research for math PhDs using techniques or using these ideas? Thinking about this technique and considering problems like Fourier components, do you think there are techniques to reduce components and improve precision? Absolutely. I think positional embeddings, we've got like we're in kind of the first inning probably on usage, and I think being able to use long context windows well, and really understand how this stuff is all working, and how it ties into, attention. I think there's so many interesting areas probably to go into in terms of like, yeah, work on different ways to use positional embeddings, different approaches to them, and absolutely.
Yeah, totally. Yeah, and I want to sort of second Jason's point there as well, which is I think Fourier analysis, in particular when it comes to positional embeddings, is really, really crucial, because you can see what folks are trying to do with rope and with some of these other, some of these other positional embedding strategies as well, is to try to solve a problem, but using, I think, methods that are, I'm not going to say simple, but using methods that are better, that have better explainability. And if we can take sort of frequency domain analysis into consideration when we're doing a lot of these positional embedding research in particular, I think it could be very, very helpful for the broader machine learning community in general. But again, that's just my 2 cents. I have a background in electrical engineering, so and one of my favorite classes in college was actually Fourier transforms. So just my 2 cents there.
Cool. Signals and systems rearing its head.
Signals and systems. Yep.
Awesome. So the takeaway on this context window is kind of this. This is the blow up you were talking about, Frank, and these just numbers are insanely massive in terms of how bad they are, versus kind of when you have the PI, you've got some amazing results with some like crazy simple addition.
Yeah.
And then the study, so this is like one, so they do kind of two approaches to like, okay, perplexity looks great, but like let's try some tasks that are harder, and actually see if it's using the context window. So this one's like the random pass key, where you have a long document, there's a pass key, and it's got to retrieve it. So it's got to use it's got to use attention going back some distance to be able to actually respond and find that item. It's almost like a memory lookup type thing. And you can see, I thought, again, the results were pretty good relative to, is it actually using the window sizes to do what's needed? This might not be the right one. This is probably the right one. Is it using the window sizes that are needed? What's the the window length based upon kind of what's the estimated window length based upon how well you're retrieving? And these all seem to be using the window length you think you could get to. And notice the this one, some of these, I guess some of the other ones are not. They also do another benchmark on, so I skipped through some section here, I think. So there's key size, there's a summarization approach as well. So they do a key lookup and a summarization on long context. So this is a benchmark on just is that small window degraded. And then here's the long document summarization. So they do a summarization. So again, let's test what we really were after in the first place, which is the long context window. Is it working and doing what we wanted to do? Again, perplexity is a nice measure, but it just does, it's not, task oriented. So this is another one, and you just, you look at the results and the results down here, and it was in the kind of top results of benchmark models too. So I felt impressed with, like, go out and use the LLaMA long context windows. They look good. Cool.
And I wouldn't be surprised if like Anthropic with their 100K models are doing this sort of internally as well. I mean, the results are really quite good. But yeah, Jason, did you want to go over the rest of the paper, or I actually have some thoughts I'd love to share as well.
Yeah, let's do that. Feel free. I think this is kind of like related where we're kind of at the end here. So yeah.
Sure. Yeah, and I will, oops, let me actually redo that real quick. And I actually want to, again, this is just general commentary here, but I actually want to draw everybody's attention to the original Vision Transformers paper. And the reason why I want to do that is I want to show, if you look in this paper, they actually talk about how they do fine-tuning at higher resolution. So I want to highlight in particular, let me do a bit of highlighting there. I want to highlight, they say here, we therefore perform 2D interpolation of the pre-trained position embeddings according to their location in the original image. So I'll explain very, very quickly what's happening here. Right? I'm a computer vision nerd, so I love talking about this stuff. If I have an image, and again, this is a vision transformer, it's 224 by 224, and I want to fine tune something larger, let's say 512 by 512, right? Vision transformers, like natural language transformers, they use positional embeddings as well. But interpolation, in this case, I believe they're doing bilinear interpolation of the embeddings. They're not actually interpolating the original sinusoidals themselves. And this is a very natural thing for computer vision, and it turns out to work very, very well. And the reason why it's so natural is because if I look at these two corners right here, as I scale the image up, these two corners actually correspond to the same regions. They actually correspond to the same information in an image. And that's why, as I do 2D interpolation for vision transform, it's a very, very natural thing to do, and it works well. There's another paper called Data Efficient Image Transformers that shows this, and I'm not going to pull that up here. But the motivation behind a lot of this work here comes from a paper called Fixing the Train Test Resolution Discrepancy from, again, folks at Facebook AI Research. I find this very, very funny because the paper that we were talking about today is from Facebook AI Research. And Hugo is one of the first authors, one of the primary authors on LLaMA 1 and LLaMA 2 as well. But just an interesting tidbit that I figured I'd share with everybody there. But that is really critical, I think, when it comes to understanding the broader machine learning world, is that there's so many ideas that can be borrowed from other modalities. And we want to be able to just keep about things with an open mind, right? Yeah, that is the point that I wanted to make sort of much earlier. But in particular, I think there's a lot of positional embeddings are sort of like black magic, and I think there's a lot of work that needs to be done, not only to understand them better, but also potentially to say, hey, how can we really use them to great effect to extend the context length of a lot of these transformers?
Yeah, awesome. I think Igor had one more question that, so it might be a little beyond me. Do you think that in this problem, we have problems like sparsity that reduce model precision, thinking about lacunarity and Fourier analysis? Can we correlate interpolation with this behavior? I actually don't know. Like, this is probably slightly beyond my comment ability. I mean, I think the use of these here is really to provide signal, signal to signal in a way that has a certain set of properties, signal to the model for each position that has some really nice properties, and depending upon your choice of positional embedding, the properties can vary a bit. And so I don't know if sparsity is kind of the issue. I haven't heard that relative to this, but there's definitely different approaches to creating these which have a whole different suites of properties. And then I've seen recent papers that combine some of them together to get joint properties. So similar to like, wavelets and Fourier analysis. I mean, there's ways of combining, decaying things with, with varying things and getting different properties. But the big idea is you're trying to focus attention and either decayed attention, focus attention, and understand position and have those be signals that the model can actually pick up, which is kind of what drives a lot of the creation of these. I don't know if I answered the question specifically, but that, maybe I skirted around the edges of it.
Yeah, I guess I suppose I don't quite understand how sparsity relates in particular to positional embeddings, but when it comes to models in general, and especially when it comes to, being a part of a vector database company, I think we're all about vector embeddings. Sparse embeddings definitely have a place when it comes to understanding not just text, not just documents, but any type of unstructured data. I think it would be a little bit harder to correlate that with Fourier analysis, but maybe there is something there as well. I don't know.
Cool. And I did want to give a plug for, there's an August 24th event in SF. So if you're local and you want to come, we'll be talking about vector databases and basically troubleshooting vector databases, and probably slightly, will be pretty technical. How do you debug embeddings? How do you troubleshoot vector databases? So definitely want to give a plug for the August 24th event in SF. If you can make time in the other 100 events you're doing in AI and SF, this is a good one to do. And thanks, Frank. And we'll kind of do more of these. And people are asking kind of where they can find details for the August 24th event. It should be, I think we do have an events page, Maggie. Our team can actually, based upon the people who attended, we'll send out maybe a link to that or something. But we should have, if I understand, I believe we have an events page, and I believe it kind of shows that there. So,
well, I will say, just
okay.
follow Arize and follow Zilla's on LinkedIn and on Twitter, and we'll be posting it there. And
Awesome.
We also have a meetup on August 10th as well. So it'll be a little bit smaller, but again, we'll have folks from both Arize as well as from Zilla's on August 10th as well as August 24th. So yeah.
And the question, I think one more person asked, when's the next community reading? I think we've been trying to do them every week, but I think we might be skipping next week. So I think it's probably 2 weeks from today. But we've been trying to do them every week. I think this one we've got one in between. So thank you, everyone. So August 16th. Sorry. Okay. All right, everyone. Thank you, Franklin. Let's definitely do another one soon.
Awesome. Looking forward to the next one, Jason.
Yeah. Thank you.